Hello, my name is Trevor Witt, and welcome to this video on using drone-based LiDAR for road and bridge inspection. So in this video, I'll talk about the basics of drone-based LiDAR, its benefits and limitations, knowing your why behind why you want to collect this data, some of the key components of this technology, including sensor settings and flight settings, as well as spatial control. I'll discuss software, and then also some other resources. So LiDAR stands for light detection and ranging. It works like radar. So radar uses sound waves to tell how far away an object is, and LiDAR does the same thing with light. So it's using a laser beam, broadcasting that laser beam, and then measuring how long it takes for it to return. And by using that, it's able to distinguish distance information. So in our case, it's using that laser to create a bunch of points or a point cloud, which ultimately gives us elevation information about the subject that we're mapping. So this is an active remote sensing technique as opposed to photogrammetry, which is passive. So this LiDAR is actually producing a signal and measuring the return of that signal. It's important to think about the differences between manned aircraft and drone-based LiDAR. Manned aircraft LiDAR has been around longer than drone-based. And a lot of the resources online, a lot of the educational materials and standards that have been developed by government agencies such as the USGS, United States Geographic Service, and the USDA NRCS also has some LiDAR standards that are out there. But these are all based on manned aircraft LiDAR. So there's some real nuances with drone-based LiDAR sensing that I will discuss in this video. So some of the benefits and limitations, the biggest thing with drone-based LiDAR is you're going to get consistent data through various lighting conditions. This is opposed to the photogrammetry method where you're reliant on a well-illuminated subject area. LiDAR doesn't need that. And then also compared to photogrammetry methods, it's much more efficient to collect and process elevation information with LiDAR. You'll see later that the amount of overlap with LiDAR is significantly reduced as compared to photogrammetry. And with a proper IMU calibration, which is absolutely critical to good LiDAR data, you have less issues for the long linear operations. So specific for road inspection or mapping, where you have a long linear stretch, that can pose some unique difficulties with photogrammetry. Whereas with LiDAR, since it's a scanning technology, it actually works fairly well. But the downsides of LiDAR, it's more expensive than photogrammetry. These sensors cost as sometimes 3 times as much as a comparable photogrammetry sensor. Usually it's 10 times or more. It's a very expensive technology compared to visual sensing. And to note, LiDAR is limited whenever you have standing water around. Just like photogrammetry, you're going to have gaps in your data set if you have standing water. So what do you want out of your data when considering using LiDAR? So you need to think about what you're not getting from photos, videos, or photogrammetry methods. It's important to try to use the simplest technology or means of data collection first before choosing something more complicated like LiDAR. And it's a good rule of thumb if you're getting to the point where you need mapping. Photogrammetry can really do anything that LiDAR can do, except for what I'll talk about a little bit later. So if you can use photogrammetry, try that first before making the jump to LiDAR. But the most likely reason to use LiDAR is for that more efficient data collection. And sometimes there's just higher trust in LiDAR. Engineers and people used to working with this kind of data, they're more familiar with LiDAR than they are with photogrammetry. So there's just a higher inherent trust in the data. And sometimes that can be reason enough. And then there's this term around canopy penetration, which is really a misnomer. There's no such thing as true penetration. You're not able to, these lasers aren't able to penetrate through a leaf or through something. Really, what that's talking about is finding gaps between leaves or gaps in the canopy to get a ground surface that's underneath that canopy. So, LiDAR produces ultimately these point clouds, which ultimately result in these different data types of either digital surface or elevation models, tins and meshes, and ultimately, really, I've always seen LiDAR ends up as a contour map. So think about what surface you're mapping, the road surface, bridge, or stockpiles. Stockpiles has been something that's come up in conversations with some of the counties here in Kansas that have been involved in this project that they're interested in doing. You have aggregate piles that you're wanting to know how much volume you have. LiDAR can be used to accomplish that. And also be thinking about who's involved, who are the stakeholders a part of the project that need to be involved in the discussions that ultimately help the data do something. So that's the pilot, the person collecting the data, engineer who's going to use it, or management using it to communicate to other stakeholders. And you need to think about how accurate you want your data and how you plan to validate that accuracy, which I'll talk about a little bit later. The biggest thing with LiDAR, really the key specification you're looking at is how many points per unit area do you need. And you have your different parameters that influence that, which are speed, altitude, scan rate, and scan pattern. Do you need your point cloud colorized? It's one of the things that not all LiDAR sensors contain a visual sensor to colorize the point cloud. But I've always found that having that color information does help with interpretation of the data. Sometimes weird things happen, and having that visual information alongside the point cloud can help clear up any, like I said, any weird things that are going on with the data. And thinking about, do you want to capture that bare earth surface below vegetation or this canopy penetration? Thinking about that. So the components of a LiDAR sensor, it's really three different things. You have the laser. Many lasers are just repurposed automotive sensors used for self-driving cars. That's really where drone-based LiDAR took off, is because those LiDAR sensors got small enough to where you could carry it on a drone. There are some companies that do now make purpose-built lasers for drone mapping. Then you've got your GPS that's measuring, your location information, and then the inertial measurement unit, which works a lot like your inner ear. It's an electronic piece of equipment that provides orientation information. This is really critical, and there's some calibration procedures to all LiDAR systems that are important to quality data. Most of these sensors are mounted fixed in place, not on a gimbal like many of the photogrammetry sensors are. And sometimes, there is a camera included along with the LiDAR to help colorize the point cloud. So some of the sensor companies, you have Regal, which is really the Bentley of LiDAR sensors. They're the name brand, they're the most expensive. Then you have some manufacturer specific LiDARs made by Wingtra and DJI. Again, all of these have to bring a combination of laser, GPS, and IMU, and which is what you see in those four other companies I have listed there. That all kind of have their secret sauce or combination of those three components. So thinking about sensor specifications, there's horizontal and vertical accuracy, also paying attention to there's specifications to the GPS and also to the IMU. There's the detection range, laser spot size. That can be really important to canopy penetration missions, to where the smaller the diameter of that spot, the more likely are you to find gaps. So that can be inherent in the sensor specification, also affected by your altitude that you're flying. You got your laser frequency and maximum returns. This is a cautionary tale. Many manufacturers will advertise 3, 5, 7 returns. as a selling point to the sensor to achieve canopy penetration. But one of the things I didn't know until working with the technology is that the further down you get in a return, the less accurate that point becomes, because it works kind of like an echo. If you're shouting into a cave, you initially hear the response sounds clear, like what your original voice sounds like, but then as it echoes through the cave, it gets more and more distorted. That's a good way to think of returns with LiDAR. So, yeah, you may be able to get a bare earth return, but that point will be so noisy that you really can't trust it. So that's my understanding at the point of this technology right now. It may get better in the future, but that's something to be critiquing of your salesperson. Ask them, okay, I've got 5 returns, but how accurate is that 5th return? Is a great question to ask. So some of your sensor settings, and some sensors are all different. It's important to know your own equipment, but be thinking about the scan pattern, the field of view of the scan. So some sensors, like I said, they're repurposed automotive LiDAR sensors where they can scan a full almost 360. You'll narrow that down to a certain field of view so that the laser isn't scanning the horizon, that you're just scanning the area kind of right below the sensor. You have scan rate and those number of returns. So even if a sensor has 3 or 5 returns, you can select it to just do that first return. Some of the flight settings. So again, here the most important, really the most important thing, or the most common thing that gets messed up in drone-based LiDAR collection, is this IMU calibration. Typically, this is a flight procedure done before, during, and after a mapping mission, because these IMUs can experience drift, which absolutely distorts the quality of the point cloud. So really pay attention to IMU calibration procedures. You got to think about your swath overlap. So this is how much each scan overlaps each other as you're mapping an area. So typically this is 20 to 50%. Really never a reason to go more than that, because again, these point clouds are so dense already. And comparing to main aircraft LiDAR, a lot of those standards I was talking about are typically used to dealing with 8 to 10 points per square meter, where drone-based LiDAR is sometimes producing hundreds of points per square meter, which ultimately is too much data that ends up getting filtered out anyways. So think about your altitude. Just like photogrammetry, it's important to know your area of interest. So if you're mapping a road, for example, in the Flint Hills where you have a lot of elevation change, you want to see if your equipment has an ability to follow that elevation while you're mapping, to where your aircraft is maintaining a constant altitude above ground instead of a constant altitude above the takeoff location. Because if it's same altitude above the takeoff location, as that elevation gets closer or further away throughout the mapped area, it will change that point cloud density. So that's an important consideration. Your speed is something you can change. And then also, it's important to consider and be mindful of your starting and ending location of your flight. You always want to try to start your flight as far away from you as possible so that it ends as close to you as possible. Because at the end of your flight, you want your battery, if you have a low battery, you want it to be closer to you rather than further away, especially with these LiDAR sensors, because they can be very expensive. So a typical workflow, another critical component to drone-based LiDAR is this setting up a GPS base station. Ideally, this is over a known location to where it's a surveyed benchmark, or you're using an in-trip connection of a base station network if you have access to one. These corrections can either be done in real time through real-time kinematic, or in post-processing kinematic. Both are viable options, but you have to have a local base or an in-trip connection to correct the GPS on board the LiDAR sensor. Thinking about the layout and survey of checkpoints, so these are your validation points throughout your area of interest. You can look towards the ASPRS standard for this, but many operators don't follow that standard because it's pretty intensive. It requires 20 plus checkpoints. Most operators aren't going to do that much. They're typically comfortable with 6 to 10. That's really up to your own departments and how much effort you want to put into these validation points. Ensure the optical window of the sensor is clean, another critical component of this type of mapping mission. You want to follow the manufacturer's recommendations for cleaning that window. Be very careful doing that. Collect the data, in-field validation, always important. Picking up your checkpoints, and then post-processing. So each one of those manufacturers, again, has their own software that's going to combine the laser returns, IMU, and GPS. And some of them make a bigger deal of strip alignment, which is that overlapping scans of the LiDAR, making sure they line up properly. That's really where you will see IMU issues. If two different strips are misaligned, likely it's an IMU problem. Big part of LiDAR data is refining and filtering and classifying the data. So typically you are going to classify ground points from any other vegetation, objects, buildings, so that you have a surface model or elevation model. I stand corrected. And you want to have that processing report to show your accuracy, to show the comparison of your point cloud to the checkpoints, and then exporting those desired products to end up going and doing something. So software, sometimes the processing software from these manufacturers also includes some analysis, but then there's a handful of other specifically built LiDAR software like LP360, TerraSolid. Those are really some name brands. You see some other ones there. That again, ultimately exporting a digital elevation model or a contour map that's going to be used in your analysis. And again, be mindful of, advocate for having a good computer to use these, because again, these files can be quite large, multiple gigabytes, so it's good to have a quality computer to work with it. What can go wrong? Again, you've heard me say this, bad IMU calibration is most typical, bad GPS, or lacking that proper correction to your base station or in-trip connection, and then having spatial control issues. I've seen GPS errors or confusion over coordinate systems. So it's important to be thinking of that. Be mindful of these other resources. Again, the ASPRS, look towards that. And then there's the 3D elevation program, kind of what I was referring to, the U.S. Geological Survey and the Natural Resource Conservation Service have some good standards. Again, they're mindful of manned aircraft LiDAR, but you can learn some things through those programs that can improve your drone-based LiDAR collection. So that concludes this video about drone-based LiDAR for road and bridge inspection.